Welcome viewers, in this video we will see the sinusoidal response of RL circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we will see the topic RL circuit sine response. If the sinusoidal is applied, what is the response of the RL circuit? Resistance and inductance. Consider a circuit consists of resistor and inductance as shown in the diagram. Now we will refer the diagram. So the sine wave is applied. Em sine omega t is the applied voltage. This is the transient current I. Switch is available. R and L is connected in series, resistor and inductor. The switch S is closed at t equal to 0. At t equal to 0, a sinusoidal voltage V cos omega t plus theta or Em sin omega t is applied to the series RL circuit, where V is the amplitude of voltage, amplitude of the wave, and theta is the phase angle. So R and L is connected in series. The switch is closed at t equal to 0. The sine wave Em sin omega t is applied to the circuit. So by using the Kirchhoff's voltage law, we can write the equation. We know that Kirchhoff's voltage law, the voltage rise equal to voltage drop. So this applied voltage is the voltage rise, Em sin omega t. That is equal to drop across resistor and inductor. That is I into R, L di by dt. So the voltage drop across these two is equal to applied voltage. So that R into I drop across in resistor plus L di by dt equal to Em sin omega t. So this is the Kirchhoff's voltage law. Applied voltage equal to drop across resistor and inductor. So here we are going to see the sinusoidal response. So we need to take the Laplace transform. Finally we need to take inverse Laplace so that we can able to find the response of the circuit. So take the Laplace transform on both the sides. Right. So while taking Laplace R into I, R is constant, I is converted into I of S. This is T domain, now converted into S domain. Similarly L into S I of S. Laplace transform of di by dt is S into I of S into Em. Em is constant. Sin omega t. Laplace transform of sin omega t is omega divided by S square plus omega square. Now Laplace transform is taken on both the sides. Take this I of S outside, commonly available. So it is R plus Ls equal to Em omega divided by sin square plus omega square. Bring this term in the denominator, that side. So that I of S equal to Em omega divided by S square plus omega square into 1 divided by R plus Ls. Right. Now we can go for the further simplification. You take this L outside. Now we are going to take the inverse Laplace. In that what we need is S plus, the standard form. Here S square plus omega square is available. Similarly here we need S is needed. S plus A, S plus B, like that. But here L is available, so L is taken outside. While taking L outside, it is R by L plus S. S into L, L is taken outside, but here L is not available, so divided. R by L plus S. So we can write it as I of S equal to Em omega divided by L. This is Em omega divided by L divided by S square plus omega square one term. S plus R by L is one term. We can take the inverse Laplace, but it is in the standard form. It should be in standard form. Then only we can take the inverse Laplace. We can take the inverse Laplace of this term alone and this term alone. We cannot take for both. So that we can use the partial fraction of this I of S. After taking partial fraction, we can easily take the inverse Laplace. Right. Now we'll see the how to take the partial fraction technique. So this is the term available. Em omega by L S square plus omega square into S plus R by L. Some standard procedure available. Accordingly it is split as K1 divided by S plus RL plus K2S plus K3 divided by S square plus omega square. Here S square there means the two terms will be there. K2S plus K3. Only S means only one term. There are 3 or 4 types available. Is coming under the third type, having S square. Right. Now see this, it is splitted into two terms. By finding the value of k1, k2 and k3, we can easily take the inverse Laplace of these two terms. This term is now converted into standard form so that we can easily take the inverse Laplace. But we need to find the value of k1, k2 and k3. Now this side the LCM is taken. We take the LCM. So here only s plus r by l is available. This term is not available. So it is multiplied. Here s square plus omega square available. This term not available. So it is multiplied. Right. So this term is multiplied here. This term is multiplied here in order to take the LCM. Right. After taking that, these two terms available on both the sides. So this is cancelled. These two terms cancel and these two terms are cancelled. We'll see after the cancellation, we'll go for the further simplification. So after cancelling these two terms, now become Em omega by L equal to K1 into S square plus omega square plus K2S plus K3 multiplied by S plus R by L. Now this is the, we'll take this equation number 1 by A. Next step, we need to find the value of K1, K2 and K3. So by substituting the value of S equal to minus R by L. See here plus R by L is there. If we substitute S equal to minus R by L, this term got cancelled. Becomes 0. So that we can easily calculate K1. So we need to identify the S value such that it is become 0. Right. So S is minus R by L means this term becomes 0. Then so that we can find K1. K2 and K3 we can find from the coefficient by equating the coefficient. Right, because here K2 and K3 both are available. So it is better to go for coefficient. So first we will substitute S equal to minus R by L. Em omega divided by L equal to K1 plus S square. So the minus become plus R square by L square plus omega square plus K2 into S is minus R by L plus K3 minus R by L plus R by L. S is minus R. Now this term become 0. Right. So what we have Em omega by L equal to K1 R square plus L square plus R square by L square plus omega square. This term is 0. Right. Now we can bring this term in the denominator. So that Em omega by L into 1 divided by R square by L square plus omega square equal to K1. Right. Now we'll go for the further simplification. So K1 equal to Em omega by L 1 divided by R square plus omega square plus L square by L square. We take this L square LCM. This LCM is taken. Here L square is available, so only R square. Here L square is not available, it is multiplied. Omega square plus L square. Right. Now this L square will go to the numerator. Em omega by L, L square divided by R square plus omega square L square. This L square one term got cancelled. So Em omega L divided by R square plus omega square into L square. So this is the K1 value. So by substituting S equal to minus R by L, we got the value of K1. Right. Some more clarification is there, simplification is there. In frequency domain, the magnitude of impedance RL circuit, impedance of RL circuit is given as Z equal to square root of R square plus omega square into L square. You square on both the sides so that Z square equal to R square plus omega square L square. Right. So that this R square plus omega L square available here can be replaced by Z square. So that K1 become Em omega L divided by Z square. Right. So after substituting Z impedance value, now we got this expression. Now we need to find K2 and K3. So consider the equation 1A. We'll consider the equation 1A. Em omega by L equal to K1 S square plus omega square plus K2S plus K3 into S plus RL. This is the equation 1A. Now we'll multiply inside this term. K2S into S, so K2S square. K2S into R by L. K2S into R by L. K3 into S. K3 R by L. Right. So this term is multiplied. Now we'll group the coefficient S square, S and constant. Em omega by L, S square. Take the S square common. Here s square term is available, k1. Here s square term k2 available. So k1 plus k2. Similarly, take s outside. Here s is available, k2 r by l. Here s is available plus k3. This k1 omega square k3 r by l is constant. So it is nothing but a quadratic equation like s square plus s plus coefficient. This is the coefficient of s square. This is coefficient of s. This is constant. Now we can equate the coefficient of s square on both the sides. Here coefficient of s square is k1 plus k2. Here s square is not available. So that is equal to 0. So k1 plus k2 equal to 0. That means k1 equal to minus k2. Right? So the k1 value we already know that. So k2 is nothing but minus of k1. Now we'll see the further simplification. Similarly, while equating the coefficient of s, coefficient of s is k2 r by l plus k3, that is equal to 0. That also 0. So here also s term is not available. So this term is become 0. From that we can find the k3 value. Right. Now we'll see k2, then we'll go for k3. So this is the coefficient of s is nothing but this term. This term is equal to 0. I will see the further. So k2 equal to minus k1. k1 we already calculated, omega l em by z square. So k2 equal to minus omega l em by z square. Now we got the k2 value also. Now can k3. For that, on equating the coefficient of s. So we already discussed this k2 r by l plus k3 is the coefficient of s, that is equal to 0. That side no coefficient available. So k3 equal to minus k2 into r by l. Minus of k2 value already available. Here also one minus is there. Minus omega l em divided by z square into r by l. So this negative, both negative become positive. This l got cancelled. So em omega r divided by z square. Now we got the value of k1, k2 as well as k3. So that can be substituted in the equation, previous equation. Then we can go for the inverse Laplace. Now we'll refer the original equation. So this is the equation I of s, k1 divided by s plus r by l plus k2s plus k3 divided by s square plus omega square. Now substitute the value of k1, k2 and k3. k1 is omega l em by z square into this term s plus r by l plus k2. k2 is minus, we know that k1 equal to minus k2 minus omega l em by z square into s plus k3. k3 is em r omega by z square divided by this term s square plus omega square. Right. Now we split this term into two terms, two different terms. So omega l em by z square, these are all constant. What we have, 1 divided by s plus r by l. So this is the standard form. Then only we can take the inverse Laplace, s by a, 1 divided by s plus a. Similarly here we can split this, minus omega l em by z square. Here s is available, s divided by s square plus omega square plus em r omega z square into 1 divided by s square plus omega square. Right. So now is brought into the standard form. This is constant, these are all constant. Here 1 divided by s plus rl, s divided by s square plus omega square. Here 1 divided by s square plus omega square. Right. Now we can easily take the inverse Laplace transform. Take inverse Laplace on both the sides. So inverse Laplace of I of s, that is nothing but I of t. Now again converted into t domain. Laplace inverse of 1 divided by s plus r by l. This is constant. And this is constant. Laplace inverse of s divided by s square plus omega square. This is constant. Laplace inverse of omega divided by s square plus omega square. So we are taking omega here, because then only we can go for sin omega t. Right. So Laplace transform of inverse of 1 divided by s plus ra. This is nothing but 1 divided by s plus a. That is nothing but e plus minus at. A is nothing but r by l. Right. 1 divided by s plus a is nothing but e power minus at. Here a is r by l. This is constant and this term constant. So s divided by s square omega square, s square plus omega square is cos omega t. This is a direct formula. Similarly, omega divided by s square plus omega square is sin omega t. Laplace inverse Laplace of omega plus omega divided by s square plus omega square is sin omega t. So now we taken all the formulas. This is nothing but 1 divided by s plus a is e power minus at. A is nothing but minus r by l. S by s square plus omega square is cos omega t. Omega divided by s square by omega square is sin omega t. Right. Now this term is constant. Em omega l divided by z square into e power minus r by l t. Not constant. This is a exponential function. Here cos omega t, sin omega t is available. Em r by z square is commonly available. So taken outside. So r sin omega t. Here r sin omega t is available. Em divided by z square is constant. Here Em divided by z square constant. Omega l is available. Minus and also minus omega l cos omega t. So this is the final expression, the transient current of the RL circuit while applying sine wave. Now we will go for further simplification in terms of impedance triangle. Now refer this triangle, right angle triangle with the resistance omega L. So this R is available. Horizontally we have RL and omega L. This is called the impedance triangle. This is angle between R and omega L. So this is the inductive reactance. So this is the impedance. The sum of these two is the impedance. Z equal to square root of R square plus omega L square. Resistance, inductive reactance, the sum of these two is the impedance. So from this triangle we can find the tan theta. Tan theta equal to opposite side by adjacent side. Omega L divided by R. From that tan pi is equal to tan inverse omega L by R. Right? We can find the pi value, angle value. Similarly cos pi equal to adjacent side by hypotenuse, R divided by Z. So from that cross multiply this, so R equal to Z cos pi. Similarly sin pi equal to opposite side by hypotenuse, omega L divided by Z. Cross multiply this, omega L equal to Z sin pi. So in the transient previous equation we got the final expression I of t. In that Z cos pi can be replaced with R. This R is replaced by Z cos pi. Similarly omega L replaced by Z sin pi. That's why we are calculating these two values, right? And also if need we can find the pi value also, angle between pi also calculated. So in this equation, previous equation, we are going to replace R with Z cos pi, omega L with Z sin pi. Right, now we'll see the further simplification. So this the previous equation, omega L Em e power minus R by Lt divided by Z square plus Em by Z square is common. Sin omega t, right? So this into R. R is replaced by now Z cos pi. Minus Z sin pi into cos omega t. This omega L is, this is a omega L. This omega L is replaced by Z sin pi, right? So this is R replaced by Z cos pi. This is omega L replaced by Z sin pi. Now it is coming under, now this Z is commonly available. You can take outside. This is nothing but sin A cos B minus cos A sin B, right? Sin A cos B minus sin B cos A. So that is nothing but this format is available. So that can be written as sin A minus B. A is omega t, B is pi. So it becomes sin omega t minus pi, right? So for the simplification we substituted R value, omega L value, Z is taken outside. So this is nothing but sin A cos B minus sin B cos A. That is nothing but sin A minus B. A is omega t, B is pi. So this is a transient term. This term is called transient term. This is the steady state term. So this is the final expression. In after substituting from the impedance triangle, we got one more equation that contain transient as well as steady state. So in this video we discuss the RL circuit with the sine wave. RL circuit with the DC circuit, DC source is available separate video. This is AC circuit. We are supplied EM sin omega t is applied. There we are applied DC voltage. So we discuss, initially we got the KVL by using KVL equation is framed, then Laplace inverse is taken. By using partial fraction techniques, we split the terms. After that inverse Laplace is taken. After simplification we got this equation. Again it is further simplified by impedance triangle. Finally we got the equation with steady state term and transient term. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.